The Monty Hall paradox. Imagine you're on a game show. In front of you are 3 doors. Behind one of the doors is a brand new car, the grand prize. Behind the other 2 doors are goats. The game show host, Monty Hall, explains the rules. You get to pick one door. After you make your choice, Monty, who knows what's behind each door, will open one of the other 2 doors to reveal a goat. Then he'll give you a choice: stick with your original door or switch to the other unopened door. What should you do? Let's say you pick door don. Monty then opens door don 3 and shows you a goat. Now you're left with a choice: stick with door don 1 or switch to door don 2. At first, it might seem like the odds are now 50-50. After all, there are 2 doors left, one with a car and one with a goat. But that's not actually the case. The surprising truth is that you have a better chance of winning if you switch doors. Here's why. When you first chose door don 1, the odds that the car was behind that door were 1 in 3, or about 33%. That means there was a 2 in 3 chance, 67%, that the car was behind one of the other 2 doors. After Monty opens one of the doors to reveal a goat, that 67% probability doesn't just vanish, it transfers to the remaining closed door. By switching, you're effectively betting on Monty's knowledge. Since he always opens a door with a goat, never the car, he's indirectly guiding you toward the winning choice. Let's break it down further with 3 possible scenarios. If the car is behind door don 1, your original pick, Monty will open one of the other 2 doors to show a goat. If you switch, you lose. If the car is behind door don 2, Monty will open door don 3 to show a goat. If you switch, you win. If the car is behind door don 3, Monty will open door don 2 to show a goat. If you switch, you win. In 2 out of 3 cases, switching will win you the car. In only 1 out of 3 cases will sticking with your original choice win. That means switching gives you a 67% chance of winning, while staying with your first choice only gives you a This result feels deeply counterintuitive. Most people's gut instinct is to assume the odds are 50-50 once a door is opened. That's why the Monty Hall paradox became so famous. When it was popularized in a magazine column by Marilyn Vos Savant in 1990, thousands of readers, including math professors, wrote in to say she was wrong. But she wasn't. The math holds up. The Monty Hall paradox challenges our natural understanding of probability and decision-making. It exposes a flaw in human reasoning known as the anchoring bias, the tendency to cling to an initial choice, even when new information suggests that the odds have shifted. It also highlights the importance of considering all available information, including the fact that Monty knows what's behind the doors and is using that knowledge to structure the game. Interestingly, the Monty Hall problem has real-world applications in fields like economics, game theory, and even medicine. For example, when doctors update a diagnosis based on new test results, they're essentially working through a version of the Monty Hall problem, adjusting probabilities based on additional information. So the next time you face a tricky decision, remember Monty Hall's game. Sometimes the smartest move isn't to trust your gut, it's to switch doors. Schrödinger's cat. Picture this. A cat is placed inside a sealed box. Along with the cat is a radioactive atom, a Geiger counter to detect radiation, a vial of poison, and a hammer. Here's how it works. If the Geiger counter detects radiation from the atom, it will trigger the hammer, which will break the vial of poison and kill the cat. But if the atom does not decay, the hammer won't drop, the vial will remain intact, and the cat will stay alive. Simple enough, right? Here's where things get strange. According to the laws of quantum mechanics, the radioactive atom is in a state of superposition. It exists in both a decayed and non-decayed state at the same time. And because the state of the cat is directly tied to the state of the atom, the cat must also be in a state of superposition. It is both alive and dead at the same time. Let that sink in for a second. The cat isn't either alive or dead, it's alive and dead simultaneously. That is, until you open the box. The moment you look inside, the cat's state collapses into one of two possible outcomes, alive or dead. But until that observation happens, the cat exists in this bizarre quantum limbo. So how did we get here? The Schrödinger's cat paradox comes from the strange world of quantum mechanics, the branch of physics that describes the behavior of particles on an atomic and subatomic scale. In the quantum world, particles don't exist in definite states the way objects in our everyday world do. Instead, they exist in a cloud of probabilities. A particle is not here or there, but rather exists in a superposition of all possible locations at once. This idea comes from the concept of the wave function, a mathematical description of a quantum system's possible states. When you measure a quantum system, the wave function collapses into a single definite state. Before you measure it, the system exists in all possible states at once. In 1935, Austrian physicist Erwin Schrödinger proposed the cat experiment as a way to highlight the absurdity of applying quantum mechanics to everyday objects. If the rules of quantum mechanics apply to subatomic particles, why wouldn't they also apply to larger objects like a cat? After all, atoms make up cats. So shouldn't the cat also exist in a state of superposition? Schrödinger's point was that this conclusion seems ridiculous. In the real world, we expect things to have definite states. A cat can't be both alive and dead at the same time. But quantum mechanics suggests that at the microscopic level, particles do exist in multiple states simultaneously. So why shouldn't this apply to larger objects too? To understand why this is so strange, let's break down the chain of events more carefully. The radioactive atom is in a state of quantum superposition. It's both decayed and not decayed. This means the Geiger counter is also in a state of superposition, both detecting and not detecting radiation. Therefore, the hammer is in a state of superposition, both falling and not falling. And that means the vial of poison is both broken and unbroken. Which means the cat is both alive and dead at the same time. But here's the kicker. This superposition only holds as long as the box remains closed. The moment you open the box and observe the cat, the superposition collapses. The cat becomes either alive or dead, but not both. The paradox of the stone. Can an all-powerful being create a stone so heavy that even it cannot lift it? At first glance, this seems like a simple question, but it creates a logical trap that challenges the very idea of omnipotence. If the being can create such a stone, then there is something it cannot do: lift the stone, which means it's not truly omnipotent. But if the being cannot create the stone, then there is also something it cannot do: creates the stone, which again means it's not truly omnipotent. Either way, the idea of omnipotence seems to crumble under the weight of the question. This is the paradox of the stone, a philosophical challenge that has puzzled thinkers for centuries. The heart of the paradox lies in the contradiction within the definition of omnipotence. Omnipotence is usually defined as the ability to do anything, no limits, no restrictions. But the moment you introduce a logically contradictory task, like creating a stone that an all-powerful being cannot lift, you create a scenario where omnipotence seems impossible to maintain. One common way to resolve the paradox is to argue that omnipotence doesn't include the ability to do the logically impossible. Just as even an omnipotent being can't make 2 + 2 = 5 or create a square circle, it also can't create a stone that it cannot lift. Under this view, the paradox is not a true limitation of power. It's simply an example of asking for something that is fundamentally nonsensical. Therefore, the inability to perform a logically contradictory task isn't a flaw in omnipotence, because the task itself is meaningless. But this raises another problem. If omnipotence is bound by logic, is it really omnipotence? If an all-powerful being can only operate within the framework of logical consistency, then it isn't truly limitless, it's just very powerful within the bounds of reason. This would mean that logic itself is a higher force than omnipotence, which seems to contradict the idea of absolute power. Philosophers like Thomas Aquinas approached this problem by redefining omnipotence. Aquinas argued that omnipotence means the ability to do all things that are possible according to the nature of an omnipotent being. In this framework, creating a stone so heavy that it cannot be lifted is not a failure of power. It's simply a meaningless task that doesn't fit the nature of omnipotence. Therefore, the paradox dissolves because the task itself is not a real test of power. Another perspective suggests that omnipotence could include the ability to limit itself. In this view, an omnipotent being could create a stone so heavy that it cannot lift it, but only by voluntarily surrendering its power to lift the stone. In this case, the act of creating the stone would demonstrate the depth of omnipotence, because it would involve the ability to impose limits on itself. But this raises a deeper question. If the being limits its own power, is it still truly omnipotent, or has it ceased to be all-powerful the moment it creates a boundary on its own? The paradox of the stone exposes a fundamental tension in the concept of power. If true omnipotence includes the ability to do the impossible, even the logically contradictory, then the concept of omnipotence itself becomes unstable and self-defeating. But if omnipotence is limited by logic, then it is no longer truly without limit. The paradox forces us to confront the boundaries of power, logic, and even the nature of existence itself. At its core, the paradox of the stone isn't just about lifting rocks, it's about the limits of human understanding. If omnipotence is beyond logic, then we may never be able to define it. And if it's bound by logic, then the concept of absolute power may be an illusion. Either way, the paradox reminds us that some questions may be too heavy for even the strongest mind to lift. The paradox of the unexpected hanging. A judge tells a condemned prisoner that he will be hanged at noon on one weekday in the coming week, but the execution will be a complete surprise. The prisoner will not know the day of the hanging until the executioner knocks on his cell door at noon that day. After hearing this, the prisoner begins to reason through the problem. He starts by thinking about Friday, the last day of the week. If he hasn't been hanged by Thursday, it would have to happen on Friday, but that wouldn't be a surprise because he would know it was coming once Thursday passed without an execution. Therefore, he concludes that he cannot be hanged on Friday. That eliminates Friday. So now the prisoner considers Thursday. If Friday is ruled out, and if he hasn't been hanged by Wednesday, then Thursday would be the only possible day left. And that wouldn't be a surprise either. Therefore, he concludes that he cannot be hanged on Thursday. Using the same logic, he eliminates Wednesday, then Tuesday, and finally Monday. By this reasoning, he concludes that the hanging is logically impossible. There is no day on which he can be hanged without it being predictable. Convinced of his airtight logic, the prisoner relaxes, confident that he has outsmarted the judge. But then, on Wednesday at noon, the executioner knocks on his door, and the prisoner is completely surprised. The judge's prediction was correct, even though the prisoner's logic seemed flawless. So, what went wrong? The paradox of the unexpected hanging is a mind-bending combination of logic, self-reference, and epistemology, the study of knowledge. The prisoner's reasoning is based on the assumption that he can anticipate the day of the execution by process of elimination. But his mistake lies in assuming that the hanging being a surprise and the logical process of elimination are compatible. The key to the paradox is that the act of being surprised itself undermines the prisoner's reason. If he fully believes the judge's statement that the execution will be a surprise, then any assumption that allows him to predict the day becomes self-defeating. The very fact that he thinks he can logically figure it out contradicts the nature of the judge's promise. Here's why. If the prisoner believes he can't be surprised because he's reasoned through every possibility, then he stops expecting the hanging altogether. But if he stops expecting it, the execution can be a surprise, and therefore the judge's statement remains valid. The paradox exposes a deep conflict between knowledge and surprise. If the prisoner could truly know the day of the execution, it would contradict the judge's promise that it would be unexpected. But if the prisoner can't know the day of the execution, then the surprise remains possible, and the execution can still happen within the rules the judge originally laid out. This paradox is similar to the famous liar's paradox. This statement is false because it involves a self-referential loop where the truth of the statement undermines itself. If the execution is logically impossible, then it becomes possible. If the prisoner cannot anticipate the execution, then it remains a surprise, which is exactly what the judge promised. Philosophers have interpreted the paradox in different ways. Some argue that it highlights the limitations of human reasoning when dealing with self-referential statements. Others suggest that the paradox reflects a deeper problem with the nature of logical certainty itself, that in certain complex systems, logical consistency may be impossible to maintain. The paradox also touches on issues of prediction and uncertainty in real life. Think about financial markets. If everyone believes that a stock will rise tomorrow, they'll buy it today, driving up the price and preventing the predicted rise from happening. Or consider political outcomes. If a poll predicts a certain candidate will win by a landslide, that expectation might affect voter turnout, thereby changing the outcome. At its core, the paradox of the unexpected hanging is about the limits of human foresight. The more you believe you can predict the future, the more likely the future is to surprise you. Sometimes the very act of trying to anticipate an outcome changes the conditions that make that outcome possible. So the prisoner's mistake wasn't in his logic. It was in thinking that logic alone could conquer uncertainty. And maybe that's the deeper lesson of the paradox. Some truths cannot be reasoned through or anticipated. Some things are destined to remain a surprise. The liar paradox. Let's suppose you're standing in front of a person who says, "This statement is false." You pause, confused. If the statement is true, then it must be false, because that's what it says. But if it's false, then it must be true, because that's the opposite of what it claims. Suddenly, your mind is trapped in an infinite loop. This is the liar paradox, a simple statement that collapses under the weight of its own logic. It's one of the oldest and most famous paradoxes in history, dating back to ancient Greece, where the philosopher Epimenides supposedly said, "All Cretans are liars." But if Epimenides himself was a Cretan, then his statement would mean that he was lying, which would mean that not all Cretans are liars. Let's carefully walk through the logical trap. Scenario 1. The statement is true. If the statement "this statement is false" is true, then it accurately describes itself as false. But that creates an immediate contradiction, because a true statement can't also be false. Scenario 2. The statement is false. If the statement is false, then it's not true that it's false, which would mean that it's actually true. Another contradiction. This self-referential loop creates a logical deadlock. No matter which way you approach it, the reasoning collapses into contradiction. It's like a snake eating its own tail. The statement destroys itself through its own structure. But why does it matter? On the surface, the liar paradox seems like a quirky brain teaser. But it actually challenges the foundations of truth and language itself. How can we define truth if some statements are true and false at the same time? This paradox helped inspire deeper questions in logic and mathematics, leading to discoveries like Gödel's incompleteness theorems, which prove that some truths can never be formally proven. The liar paradox also touches on the limits of human understanding. If language can produce contradictions this easily, how much of what we believe to be true is built on shaky ground? Even in everyday life, we encounter liar-type paradoxes. Politicians claiming, "I'm always honest," or a friend saying, "I never lie." If they're telling the truth, they might be lying. If they're lying, they might be telling the truth. So what's the takeaway? The liar paradox teaches us that truth isn't always as simple as it seems, and that sometimes the hardest part of understanding reality is knowing where the loop begins and where it ends. The paradox of Achilles and the tortoise. Imagine the great Greek hero, Achilles, the fastest runner in the world, racing against a slow-moving tortoise. To keep things interesting, the tortoise is given a head start of, say, 10 meters. Achilles, confident in his speed, sets off after the tortoise. But here's where the paradox begins. To catch up to the tortoise, Achilles first has to reach the spot where the tortoise started. But by the time Achilles reaches that point, the tortoise has moved a little farther ahead. Achilles then has to reach that new spot. But by the time he does, the tortoise has again inched forward. No matter how quickly Achilles closes the gap, the tortoise is always just a little bit ahead. The paradox, first proposed by the ancient Greek philosopher Zeno of Elea, suggests that Achilles will never actually catch the tortoise. This is because Achilles must first cover an infinite number of smaller and smaller distances, each one taking a finite amount of time. Since there's an infinite number of steps to take, Achilles would require an infinite amount of time to catch up, even though we know from experience that a faster runner will eventually overtake a slower one. To understand why this is so strange, consider how the race breaks down mathematically. Achilles first runs the 10 meters to the tortoise's starting point. While he's doing that, the tortoise might move 1 meter. Achilles then runs that extra meter, but in that time, the tortoise has crept ahead by, say, 10 centimeters. Achilles closes that gap, but the tortoise has moved 1 centimeter more, and so on. Each gap gets smaller, but there's always a new, smaller gap left to close. It seems like Achilles is stuck in an eternal loop of catching up, even though we know logically that he should pass the tortoise fairly quickly. Zeno's paradox challenges our basic understanding of motion and time. If space and time are infinitely divisible, how can Achilles ever finish closing the gap? The solution to the paradox didn't come until thousands of years later, with the development of calculus by Isaac Newton and Gottfried Leibniz. They showed that an infinite series of progressively smaller distances can still sum to a finite value. In other words, even though Achilles has to complete an infinite number of steps to catch up with the tortoise, the total time he spends doing so converges to a finite limit. After Achilles closes that gap, the time to close the next gap is smaller, and so on. But when you sum all those times, the total follows the formula for an infinite geometric series, which converges to a finite value. But Zeno wasn't wrong to identify a deep problem. The paradox forces us to confront the strange nature of infinity and continuity. If space and time are infinitely divisible, how can any motion occur at all without getting lost in an infinite sequence of steps? The mathematical solution suggests that motion is possible, because the sum of the infinite series remains finite, but the philosophical question lingers. What does it really mean to say that space and time are continuous? Quantum physics adds another layer to this puzzle. At the smallest scales, space and time might not actually be continuous. They might be made up of discrete quanta, like the pixels on a screen. If that's true, Achilles wouldn't have to complete an infinite number of steps to catch the tortoise, because there would be a smallest possible unit of distance and time. Motion would happen not in a smooth flow, but in tiny jumps. Zeno's paradox also raises questions about the nature of perception and reality. If Achilles clearly catches the tortoise in the real world, but the math suggests an infinite sequence of events. Which one reflects the true nature of reality? Are we just experiencing an illusion of continuous motion, or is the concept of infinity baked into the fabric of the universe? The paradox of Achilles and the tortoise is more than just a clever thought experiment. It's a window into the fundamental nature of space, time, and motion. Zeno's paradox reminds us that the world we experience might not align perfectly with the rules of logic and mathematics, and even if we can solve the math, the philosophical mystery of infinity remains. The omnipotence paradox. Let's suppose an all-powerful being, a godlike entity with limitless power, stands before you. This being claims, "I am truly omnipotent. I can do anything." You pause, thinking carefully. Then you ask a simple but devastating question. Can you create a task so impossible that even you cannot complete it? If the being can't create such a task, then it isn't truly omnipotent, because there's something it can't do. But if it can create such a task and then can't complete it, then it still isn't truly omnipotent, because there's something it can't accomplish. This is the omnipotence paradox, a challenge to the very definition of ultimate power. Let's break down the logical trap step by step. Scenario 1. The being cannot create the impossible task. If the being cannot create a task that it cannot complete, then it is not all-powerful, because true omnipotence should include the ability to create anything, even an impossible task. This would mean the being's power is limited. Scenario 2. The being creates the task, but cannot complete it. If the being creates a task that it cannot complete, then it has demonstrated a limit to its power, because true omnipotence should mean the ability to accomplish anything, including solving impossible problems. By failing to complete the task, the being exposes a limit to its supposed omnipotence. Why does it matter? The omnipotence paradox exposes the logical contradictions that arise when you try to define absolute power. Can an all-powerful being be bound by the laws of logic? Or would true omnipotence mean the ability to defy logic itself? Some philosophers resolve the paradox by redefining omnipotence. They argue that true omnipotence isn't about doing the logically impossible, like creating a square circle or making 2 + 2 = 5, but about the ability to do anything that is logically possible. Under this definition, the paradox disappears because creating an unsolvable task is inherently a contradiction, like dividing by 0. Others take a more radical approach, suggesting that an all-powerful being could operate beyond the limits of logic itself. If omnipotence includes the ability to reshape reality, then logical consistency might not apply. In that case, the being could both create the impossible task and complete it, because logic would no longer be a limiting factor. The paradox also raises profound questions about human understanding of power and limits. Is the idea of absolute power even coherent, or are we simply projecting our limited understanding of the universe onto a concept that defies explanation? The omnipotence paradox teaches us that power, like truth and identity, may not fit neatly into human logic, and that some questions about existence and reality might be unanswerable by the human mind. The paradox of Buridan's ass. Imagine a donkey standing perfectly between two identical piles of hay. The donkey is hungry, but each pile of hay is equally appealing. The same size, same smell, same distance. Since there's no reason to prefer one pile over the other, the donkey finds itself paralyzed, unable to decide which way to go. Eventually it starves to death. Not because food wasn't available, but because the absence of a clear reason to choose one pile over the other left the donkey stuck in indecision. This is the paradox of Buridan's ass, named after the 14th century philosopher Jean Buridan. Although it actually has roots in the thinking of Aristotle, it's meant to illustrate the limits of rational decision-making when faced with perfectly balanced choices. If two options are completely identical in value and consequence, How can rationality provide a reason to choose one over the other? And if rationality can't resolve the choice, does that mean that true rational behavior would lead to paralysis? At first glance, the paradox might seem ridiculous. After all, real-life decisions are almost never perfectly balanced. But Buridan's ars raises deeper questions about the nature of free will, rationality, and decision-making. It challenges the assumption that rational decisions are always possible, and that logical reasoning can resolve any conflict. Let's explore why this situation creates a logical deadlock. Classical decision theory holds that a rational agent will always choose the option that maximizes utility, the greatest benefit or least harm. If two options provide exactly the same utility, then decision theory predicts that there's no basis for choosing one over the other. In that case, the logical conclusion is that the agent should remain indecisive, which for the donkey means starvation. But this leads to an uncomfortable conclusion. If rationality cannot provide a reason to choose between two equal options, does that mean that rationality itself is incomplete or flawed? Should a truly rational agent sometimes choose randomly, even if randomness seems to contradict the idea of rational decision-making? One response to the paradox is to argue that true rationality requires some degree of flexibility or irrationality. If two options are perfectly balanced, a rational agent might need to rely on something beyond pure logic, intuition, instinct, or even randomness to break the deadlock. In the case of the donkey, this would mean just picking one pile of hay at random. But if randomness becomes a legitimate decision-making tool, does that undermine the idea of rationality itself? Another interpretation suggests that perfect balance between two options is an illusion. In reality, there's always some difference, even if it's microscopic or subconscious, a slightly stronger smell, a fraction of a second difference in reaction time, or a hidden preference. The paradox might simply highlight the fact that true perfect balance almost never exists in the real world. But Buridan's ars also raises deeper philosophical questions about the nature of free will. If rational decision-making requires a clear reason to act, then cases of perfect symmetry leave no room for action. Does that mean that free will, the ability to choose without a clear reason, requires some form of irrationality or arbitrariness? If so, does true freedom come not from rationality, but from the ability to act without justification? This paradox echoes real-life situations where indecision can be paralyzing. Think about standing in front of two nearly identical products at a store, unable to decide which to buy, or facing two equally appealing job offers, unsure which path to take. Rational analysis might not help you because the options are too balanced, and the more you think about it, the harder the decision becomes. Psychologists have explored this effect and found that too much choice often leads to decision paralysis. When options are balanced, the fear of making the wrong choice increases, and the brain struggles to justify any particular decision. This is why companies often limit choices or use subtle psychological cues to push consumers toward a preferred option. They know that too much balance leads to hesitation. So, is there a solution to Buridan's? Some philosophers argue that randomness is the answer, that when reason provides no basis for a decision, a rational agent should introduce randomness as a way to break the tie. Others argue that rationality isn't about perfect symmetry, that even the slightest hint of difference, conscious or unconscious, can be enough to resolve the choice. But perhaps the deeper lesson of Buridan's ars is that rationality alone isn't enough to navigate the complexity of life. Sometimes action requires more than reason. It requires trust in instinct, acceptance of uncertainty, and the willingness to take a leap without knowing exactly why. The paradox suggests that pure logic might not be the ultimate guide for human behavior. Sometimes the path forward isn't about finding the perfect reason. It's about recognizing that movement, even without certainty, is better than standing still. The grandfather paradox. Imagine you've just invented a time machine. Excited by the possibilities, you decide to travel back in time. not to meet historical figures or explore ancient civilizations, but to test a disturbing idea. What if I traveled back in time and prevented my grandfather from ever meeting my grandmother? You step into the machine, set the date, and find yourself decades before you were born. You track down your grandfather and stop him from meeting your grandmother. Now comes the problem. If your grandparents never meet, your parent is never born. If your parent is never born, you are never born. And if you were never born, you could never have traveled back in time to prevent them from meeting in the first place. This is the grandfather paradox, a mind-bending loop that exposes the logical contradictions of time travel. Let's walk through the scenarios, step by step. Scenario 1. You prevent the meeting. If you successfully prevent your grandparents from meeting, then you erase your own existence. But if you were never born, how could you have traveled back in time to stop them from meeting? The moment you succeed, you create a contradiction. Your very action wipes out the possibility of that action ever occurring. Scenario 2. You fail to prevent the meeting. Maybe you slip on a banana peel at the last second. Or maybe fate conspires against you. A random event stops you from interfering. In this case, your grandparents still meet, your parent is born, and so are you. This scenario avoids the paradox, but it suggests that the past is somehow fixed or protected from interference. Why does it matter? The grandfather paradox challenges our understanding of causality, the idea that every effect has a cause. If time travel allows you to change the past, it introduces a causal loop, where the effect, your time travel, erases the cause, your birth. But if time travel doesn't allow you to change the past, then what's the point of traveling through time at all? Physicists and philosophers have wrestled with this paradox for decades. Some suggest that time travel might operate under a self-consistency principle, meaning that events would automatically correct themselves to prevent contradictions. In that case, you could visit the past, but something would always prevent you from altering it in a way that creates a paradox. Others propose the many worlds hypothesis, the idea that altering the past creates a branching timeline or parallel universe. In that case, you wouldn't erase yourself, you would simply shift into an alternate timeline where you were never born. The grandfather paradox also raises deeper questions about free will and fate. If the past is fixed and you can't change it, do you really have control over your actions, or is the timeline locked in place, with your decisions predetermined? The grandfather paradox teaches us that time might not work the way we think it does, and that some questions about the nature of reality might be impossible to resolve within the limits of human understanding. The ship of Theseus paradox. Imagine an ancient ship, the legendary ship of Theseus, docked in a harbor. Over time, the ship's wooden planks begin to rot, so the crew replaces them one by one. Eventually, every single plank, sail, and rope has been replaced. Now ask yourself, is this still the same ship? At first, it seems reasonable to say yes. After all, the ship looks identical, and each replacement happened gradually. But what if someone had collected all the original rotting planks and reassembled them into a second ship? Now there are two ships, one made entirely of new parts, and one made entirely of the original materials. So which one is the real ship of Theseus? This is the ship of Theseus paradox, a philosophical puzzle that questions the very nature of identity and change. Let's explore the two possible perspectives. Scenario 1. The ship with new parts is the real ship. In this view, the identity of the ship is tied to its function and continuity. Since the crew gradually replaced each part while maintaining the ship's purpose, the ship remained the ship of Theseus the entire time. This argument suggests that identity isn't about physical components. It's about the role an object plays over time. Scenario 2. The ship rebuilt with original parts is the real ship. In this view, the identity of the ship is tied to its physical material. Since the original planks, nails and ropes have been restored, this reassembled ship is the true ship of Theseus, even if it had been temporarily disassembled. Both perspectives reveal something surprising. Identity may not have a clear-cut answer. Why does it matter? The ship of Theseus paradox goes far beyond ships. It touches on questions of identity in people, objects, and even ideas. Consider your own body. Nearly all of your cells are replaced over the course of several years. Are you still the same person you were 10 years ago? Or consider organizations. If a company replaces all its employees, updates its logo, and shifts its mission, is it still the same company? The paradox also appears in modern technology. Imagine a car that has every part replaced. Is it still the same car? What about digital data? If you back up your phone, then buy a new device and restore your data, is it still your phone? Some philosophers suggest that identity is an illusion, that the sense of continuity we feel is merely our mind stitching together fragments of experience. Others argue that identity is less about physical pieces and more about memory, function, or purpose. The ship of Theseus paradox teaches us that identity isn't always black and white. Sometimes it's a matter of perspective. And perhaps the most meaningful answer isn't which version is correct, but what we choose to believe makes something or someone truly themselves. The barber paradox. Let's suppose you live in a small village with a single barber. The barber has a very specific rule. I shave all men in the village who do not shave themselves, and only those men. One day, you start thinking about a troubling question: who shaves the barber? At first, it seems like a simple problem. If the barber shaves himself, then by the rule he shouldn't be shaving himself, because he only shaves men who don't shave themselves. But if the barber doesn't shave himself, then by the rule he should be shaving himself, because he shaves all men who don't shave themselves. No matter how you try to resolve it, you end up with a contradiction. This is the barber paradox. First proposed by the mathematician Bertrand Russell as a way to highlight the problems of self-reference and set theory. Let's carefully work through the two possible scenarios. Scenario 1. The barber shaves himself. If the barber shaves himself, then he breaks his own rule, because he's only supposed to shave men who don't shave themselves. So he can't shave himself. Scenario 2. The barber doesn't shave himself. If the barber doesn't shave himself, then he falls into the category of men in the village who don't shave themselves, which means the barber should be shaving him. But if the barber shaves himself, we're back to the original contradiction. The problem is that the barber both is and is not part of the group of men that he is supposed to shave. This creates a logical loop that collapses under the weight of its own rules. Why does it matter? The barber paradox isn't just a quirky puzzle. It exposed a deep flaw in early set theory. Russell originally used it to challenge the idea that you could create a set of all sets that don't contain themselves. If such a set exists, does it contain itself or not? If it contains itself, it contradicts the rule. If it doesn't, it should contain itself. This seemingly simple logical conflict helped lead to the development of more sophisticated foundations in mathematics and logic. But the paradox also raises deeper philosophical questions. Can systems of rules be consistent and complete at the same time? Are there limits to logical systems, places where consistency breaks down into contradiction? Even in real life, we encounter barber-like contradictions. Think about legal systems with conflicting rules or social norms that contradict each other depending on the situation. Who decides what the correct solution is when the rules don't align? The barber paradox teaches us that not every problem has a clean answer, and sometimes the real challenge isn't solving the puzzle, but recognizing that the rules themselves might be flawed. The Raven paradox. Imagine a scientist wants to test the hypothesis that all ravens are black. This seems simple enough. You could confirm it by observing ravens and checking if they are black. Suppose the scientist examines a raven and it's black. That seems to support the hypothesis. Then they observe another raven, also black. More evidence. But here's where things get strange. According to the logic of confirmation, any evidence that supports a general statement should also support its logical equivalent. The statement "all ravens are black" is logically equivalent to "if something is not black, then it is not a raven." This is called a contrapositive, and in logic, a statement and its contrapositive are always equally true. This means that if finding a black raven supports the hypothesis, then observing something that is not a raven and not black, like a green apple, should also support the hypothesis. If you see a green apple, it confirms that the object is not black and not a raven, which logically aligns with the statement "if something is not black, it is not a raven." Therefore, every green apple, every red flower, every white cloud, all of them technically count as supporting evidence for the idea that all ravens are black. This is the heart of the raven paradox, first introduced by the German philosopher Carl Gustav Hempel It exposes a strange contradiction in the way scientific reasoning and logical confirmation work. On the surface, it seems ridiculous to claim that seeing a green apple tells you something about the color of ravens, but if you follow the rules of formal logic, that's exactly what it suggests. The problem lies in the fact that our intuitive understanding of confirmation clashes with the rules of formal logic. When we see a black raven, it directly supports the hypothesis because it's an example of what the hypothesis predicts. But when we see a green apple, it doesn't feel like it tells us anything meaningful about ravens, even though it technically fits the logical criteria for confirming the contrapositive. Philosophers have proposed different solutions to this paradox. Some argue that the problem is statistical. Seeing a green apple is meaningless because it doesn't raise the likelihood that all ravens are black. After all, there are countless non-ravens in the world, and most of them aren't black. So seeing a green apple is just one more piece of trivial data in a sea of unrelated objects. Others suggest that the paradox arises from the difference between logical confirmation and psychological confirmation. While logic says a green apple should confirm the hypothesis, our minds are wired to find direct, causal evidence more convincing. Seeing a green apple simply doesn't have the same psychological weight as seeing a black raven, even if, under strict logical reasoning, they're equally valid. Hempel's paradox raises bigger questions about how we gather knowledge and test scientific theories. In science, we often assume that confirming evidence is valuable, but how much of that is rooted in logic, and how much is based on human intuition and pattern recognition? If a green apple can count as evidence for the color of ravens, then maybe the process of forming knowledge is less straightforward than we think. The raven paradox challenges the very foundations of scientific reasoning, forcing us to reconsider how we define evidence, and whether logic alone is enough to explain how we know what we know. The prisoner's dilemma. Let's step into a cold, dimly lit interrogation room. Two suspects sit in separate rooms, handcuffed to metal chairs. They've been accused of a serious crime, let's say a bank robbery, but the evidence is weak. The police don't have enough to convict unless one of them confesses, so the detectives present them with a choice, a brutal game of strategy and trust. Here's how it works. Each prisoner is given two options: cooperate with the other prisoner and stay silent, or betray the other prisoner and confess to the crime. If both prisoners stay silent, they'll each receive a light sentence of 1 year in prison, a show of solidarity paying off. If one prisoner betrays the other while the other stays silent, the betrayer walks free while the silent prisoner gets the maximum sentence of 5 years. But if both betray each other, they each get 3 years in prison. The catch? They have no way of communicating with each other. They have to make the decision alone, without knowing what the other will do. Let's break down the possible outcomes. If both cooperate and stay silent, they each get 1 year. If one betrays while the other stays silent, the betrayer walks free, and the silent prisoner gets 5 years. If both betray each other, they each get 3 years. On the surface, the logical choice seems obvious. They should both cooperate and stay silent. That way they both minimize their prison time. But here's where the dilemma arises. From an individual perspective, betrayal is the more rational choice. If the other prisoner stays silent, betraying means you walk free. If the other prisoner betrays you, betraying back ensures you don't suffer the worst possible outcome. Betrayal is the safest bet from a purely self-interested perspective. But when both prisoners follow this logic, they end up with a worse collective outcome than if they had cooperated. Let's walk through the logic from the perspective of one prisoner. Say you decide to stay silent, trusting your partner to do the same. If they betray you, you're left with the harshest penalty of 5 years in prison. But if you betray them first, the worst you'll face is 3 years. Or if they stay silent, you'll walk free. Either way, betrayal looks safer. Now consider, the other prisoner is thinking exactly the same thing. Both of you choose the rational self-interested action, and both of you end up with 3 years instead of the 1 year you could have had through cooperation. This is the brutal core of the prisoner's dilemma. Rational individual decisions lead to worse outcomes for everyone. Acting in your own self-interest seems logical, but when both parties do it, it creates a collectively worse outcome. The prisoner's dilemma isn't just a hypothetical thought experiment. Its logic plays out in real life, in economics, politics, relationships, and even global conflicts. Think about environmental issues. If all countries cooperate and cut carbon emissions, the planet benefits and climate change slows down. But if one country cuts emissions while others continue to pollute, that country risks weakening its economy while the others benefit. So the rational choice is to keep polluting. But if every country follows that logic, the planet suffers and everyone loses. Or consider nuclear disarmament. If two rival nations both agree to reduce their nuclear arsenals, global security improves. But if one disarms while the other secretly holds on to its weapons, the disarmed nation becomes vulnerable. The rational choice is to keep nuclear weapons, but if both sides follow this logic, you get an arms race and heightened risk of global destruction. Even relationships and business deals reflect the prisoner's dilemma. Let's say you and a friend agree to start a business. If both of you work hard and share profits fairly, you both succeed. But if one of you slacks off or siphons money while the other works hard, the betrayer benefits while the other suffers. So the rational move is to protect yourself and work less or take more. But if you both follow this logic, the business collapses and you both lose. The brilliance of the prisoner's dilemma is that it exposes a fundamental tension between individual rationality and collective benefit. Cooperation leads to better outcomes for the group, but individual self-interest drives people toward betrayal. And here's the real kicker. Once trust is broken, it's hard to restore. If two prisoners betray each other, they'll likely betray each other again in future situations. Cooperation requires a leap of faith, trusting that the other party will act in good faith even when the self-serving option looks more tempting. Game theory, the field of mathematics and strategy that studies the prisoner's dilemma, has explored variations of this problem. One famous version is the iterated prisoner's dilemma, where the game is repeated multiple times. In this version, cooperation becomes more likely over time because both parties have the chance to retaliate or reward each other in future rounds. If you betray me today, I can betray you tomorrow. So repeated interactions create an incentive for trust and cooperation to emerge. The most successful strategy for the iterated prisoner's dilemma was discovered by political scientist Robert Axelrod in the It's called tit for tat. You start by cooperating, and then you mirror the other player's last move. If they cooperate, you cooperate. If they betray, you. This strategy builds trust, but also enforces accountability, a delicate balance of reward and punishment that fosters cooperation over time. The prisoner's dilemma raises deep philosophical questions about human nature and morality. Are we fundamentally selfish, driven by self-interest even at the expense of others, or are we capable of rising above short-term gain to achieve collective? History shows that human societies thrive when cooperation and trust are strong. But those bonds are fragile and easily undermined by fear and greed. Perhaps the most important lesson of the prisoner's dilemma is that cooperation isn't just a moral ideal, it's a strategic advantage. The world's most successful societies, businesses, and relationships are built on trust, reciprocity, and the understanding that short-term sacrifice often leads to long-term gain. But cooperation requires courage, the willingness to resist the easy, selfish move, and trust that the other person will do the same. So next time you find yourself in a situation where betrayal seems like the smartest move, a business deal, a relationship, or even a political decision, remember the prisoner's dilemma. Sometimes the rational move isn't the winning one. Sometimes the best strategy isn't to act alone, it's to trust the other person and hope they trust you back. The Sorites paradox. Imagine a single grain of sand sitting on the ground. It's clearly not a heap, it's just one grain. Now, suppose you add another grain of sand next to it. It's still not a heap, right? You add another, still not a heap. You keep adding grains, one by one. At some point, you have a large pile of sand. But here's the question. At what exact point did it become a heap? This is the Sorites paradox, a problem that arises from vague concepts and definitions. The term Sorites comes from the Greek word soros, meaning heap. The paradox was first proposed by the ancient Greek philosopher Eubulides, the same mind behind the liar's paradox. The logic behind it seems straightforward at first. A single grain of sand is clearly not a heap. If you add one more grain, it's still not a heap. If adding a single grain to a non-heap never creates a heap, then logically, no matter how many grains you add, you should never end up with a heap. But this is clearly wrong, because at some point, a large pile of sand is undeniably a heap. The contradiction lies in the fact that adding a single grain of sand seems to make no meaningful difference, and yet, eventually, a collection of grains becomes a heap. So when exactly does that transition happen? If you try to define a precise point where a heap begins, you run into trouble. Is it at 100 grains? 1,000 grains? 10,000 grains? Any number you choose seems arbitrary, and yet a heap somehow emerges from the gradual process of adding grain. The Sorites paradox highlights the problem with vague terms. Words like heap, bold, rich, or tall don't have clear boundaries. If someone has 100,000 hairs, they aren't bald. But if you pluck one hair at a time, when do they become bald? If you have 1,000, you aren't rich. But if you keep adding money, when exactly do you become rich? If you're young at 20 and old at 80, at what precise age do you stop being young and start being old? Philosophers have tried to resolve this paradox in different ways. Some argue that vague terms simply don't have sharp boundaries, and that's okay. Language works because we share a rough understanding, even if the edges are blurry. This view, called supervaluationism, suggests that terms like heap are meaningful even if there's no clear cutoff point. Others, known as epistemicists, claim that there actually is a precise point where a heap begins. We just don't have the knowledge or precision to identify it. Somewhere between 5,000 and 5,001 grains of sand, the transition happens, but it's beyond human perception. Another view, called degree theory, suggests that vague concepts exist on a spectrum. A heap isn't a binary state, it's a gradual transition where the term becomes more applicable over time. The Sorites paradox reveals that language and meaning are often built on imprecise foundations, and yet we function perfectly well using these vague terms every day. We know what a heap of sand looks like, even if we can't define the exact number of grains that make it one. This suggests that human understanding isn't rooted in rigid definitions, but in a shared, flexible interpretation of the world. In the end, the Sorites paradox isn't just about sand, it's about how we make sense of complex, ambiguous realities, and why language, despite its imperfections, works so well in helping us navigate the world. The Banach-Tarski paradox. Imagine you're holding a perfect solid sphere in your hands, like a smooth, polished marble. Now imagine you could break that sphere into a finite number of pieces, let's say 5 or 6, and with a bit of mathematical magic, you could reassemble those pieces into 2 identical spheres, each exactly the same size as the original one. You haven't stretched, shrunk, or added any new material, you've simply rearranged the parts. Sounds impossible, right? Welcome to the Banach-Tarski paradox, one of the most mind-bending and counterintuitive results in the history of mathematics. To understand why this is so shocking, let's start with the basic principle of conservation. In everyday life, when you cut an object into pieces and put it back together, the total volume stays the same. If you cut a cake into slices and put the slices back together, you don't magically end up with 2 cakes. You've still got the same amount of cake, unless you're dealing with some very suspicious bakery magic. But the Banach-Tarski paradox claims that, under certain mathematical rules, you can split a solid sphere into a finite number of pieces and reassemble them into 2 spheres of the same size as the original. In other words, you've doubled the volume without adding any new material. This result was first proposed in 1924 by 2 Polish mathematicians, Stefan Banach and Alfred Tarski. It's based on the strange and surprising properties of infinity, specifically the nature of sets and how they behave under certain types of mathematical operations. To see how this works, we need to take a quick dive into the world of set theory and geometric transformation. The key to the Banach-Tarski paradox lies in something called the axiom of choice, a foundational principle in mathematics that says that given any collection of sets, you can construct a new set by choosing exactly one element from each set. That sounds innocent enough, but it has some bizarre consequences when applied to infinite sets. Here's how the Banach-Tarski process works. Conceptually, don't try this at home. Start with a solid sphere. Divide the sphere into 5 separate pieces. Some of these pieces will be constructed in extremely complex, fractal-like patterns, so complex that they cannot be properly measured in terms of volume. Apply a series of rotations and translations to these pieces without stretching or distorting them. Magically, you can now rearrange these 5 pieces into 2 spheres, each identical in size to the original. At this point, you might be wondering, how is this even possible? How can you create 2 objects from one without breaking the laws of physics? The answer lies in the nature of infinity, and the fact that the pieces involved are not ordinary, well-behaved shapes. They are mathematically pathological. The pieces involved in the Banach-Tarski paradox are what mathematicians call non-measurable sets, objects that cannot be assigned a standard volume in the usual sense. When you divide a sphere into these non-measurable sets and apply rotations and translations, you aren't really duplicating the sphere in a physical sense. Think of it like this. Imagine you have an infinite set of points, say the set of all integers. If you double that set by creating a new set containing all even numbers, which is a subset of the original, you still have an infinite set. Infinity doesn't behave like normal numbers. It's not bound by the same rules of conservation. The Benach-Tarski paradox shows that this weirdness extends not just to sets of numbers, but to actual geometric objects in three-dimensional space. Of course, this doesn't mean you could walk into a lab and actually perform the Benach-Tarski process with physical objects. The paradox relies on mathematical idealizations that don't exist in the physical world. Real objects are made of atoms, which have definite sizes and positions, and you can't slice them up into infinitely small or non-measurable pieces. But in the abstract world of pure mathematics, where sets can be infinitely divisible and transformations can be perfectly precise, the Benach-Tarski paradox is completely valid. This paradox reveals something profound about the nature of infinity and the limits of our intuitive understanding of space and volume. It suggests that our everyday experience of objects and measurement breaks down when we enter the realm of the infinite. In a sense, the Benach-Tarski paradox shows that volume itself, something we think of as a fundamental property of objects, is not as concrete or stable as it seems. The paradox also highlights the strange consequences of the axiom of choice, a seemingly harmless mathematical principle that allows for the construction of sets in a way that defies physical intuition. Some mathematicians have even questioned whether the axiom of choice should be accepted at all, given that it leads to such bizarre and counterintuitive results. But most mathematicians accept it because it allows for powerful and elegant proofs in many areas of mathematics, even if it produces some unsettling consequences, like the Benach-Tarski paradox. Interestingly, the Benach-Tarski paradox only works in 3 or more dimensions. In 2 dimensions, say if you try to cut up a circle instead of a sphere, you can't perform the same trick. This suggests that the paradox isn't just about infinity, it's about the complex structure of 3-dimensional space itself. So what's the deeper lesson here? The Benach-Tarski paradox challenges our basic notions of space, volume, and reality. It shows that mathematics doesn't always align with our physical intuitions, and that the world of infinity operates under its own set of rules. In the physical world, you can't create 2 oranges from 1 orange, but in the mathematical universe, the boundaries of what's possible are much more fluid. At its core, the Benach-Tarski paradox is a reminder that mathematics isn't just a tool for describing the world, it's a window into a deeper and stranger reality, where the rules we take for granted might not hold. And maybe that's the most mind-bending part of all, that beneath the solid, measurable world we experience every day lies a hidden realm where infinity plays by its own mysterious rules. The twin paradox. Imagine 2 identical twins, Alice and Bob. Alice decides to embark on a high-speed journey through space, while Bob stays on Earth. Alice's spaceship travels at near light speed for 30 years before she returns home. When she steps out of the spaceship, Bob is shocked. Alice looks younger than him, even though they were born at the same time. How is this possible? This is the twin paradox, which emerges from Einstein's theory of special relativity. According to special relativity, time slows down for objects moving at high speeds. This effect is called time dilation. The faster you move, the slower time passes for you relative to someone who is stationary. Here's how it works. From Bob's perspective, Alice's spaceship is moving at near light speed, so time should be running more slowly for her. While Bob might experience 20 years on Earth, Alice, traveling close to the speed of light, might only experience, say, that explains why Alice appears younger when she returns. But here's where the paradox emerges. From Alice's point of view, she could just as easily argue that Bob was the one moving. After all, in the framework of special relativity, motion is relative. If Alice sees herself as stationary and the Earth as moving away at near light speed, wouldn't that mean time should be running more slowly for Bob? If that's true, Bob should be younger than Alice when they reunite, which creates a contradiction. How can they both be younger than each other at the same time? The resolution lies in the fact that Alice's experience isn't symmetric to Bob's. While Bob remains in an inertial, non-accelerating frame of reference, Alice's journey involves acceleration. When Alice turns her spaceship around to return to Earth, she experiences a shift in reference frames. That acceleration breaks the symmetry between them. Alice is not in a purely inertial frame throughout the journey. She feels the forces of acceleration, while Bob stays in an inertial frame. Mathematically, this is explained by the equations of special relativity. The key factor is the Lorentz factor, which measures how much time dilation occurs based on the speed of travel. The faster Alice travels relative to Bob, the greater the effect of time dilation. The acceleration Alice experiences during the turnaround introduces a shift in the passage of time that gives Bob the age advantage when they meet again. To put it another way, time dilation only works symmetrically when both observers remain in uniform motion. But the moment Alice accelerates to change direction, the symmetry is broken, making Bob's clock run faster relative to Alice's. That's why Alice is younger when they finally reunite. The twin paradox highlights the strange and counterintuitive nature of time under relativity. It reveals that time is not an absolute universal constant. It's flexible, influenced by speed and gravity. This is more than just a theoretical puzzle. The effects of time dilation have been proven through experiment. Atomic clocks placed on fast-moving jets have been shown to tick more slowly compared to identical clocks left on the ground, confirming Einstein's predictions. Even GPS satellites which orbit the Earth at high speeds have to account for time dilation. If the onboard clocks weren't adjusted to compensate for the effects of both their speed and the weaker gravitational field of space, GPS readings would drift by several kilometers per day. The twin paradox forces us to reconsider our intuitive understanding of time. Time isn't universal. It bends and stretches depending on how fast we move and how much gravity we experience. The idea that two people, starting from the same moment, could age at different rates challenges our deepest assumptions about the nature of reality. The Zeno paradox. Imagine you're standing at the starting line of a race. Your goal is to reach the finish line. Simple enough, right? But now let's apply the logic of Zeno of Elea, an ancient Greek philosopher who proposed a seemingly impossible problem. To reach the finish line, you first have to cover half the distance to the end. Once you reach that halfway point, you then need to cover half of the remaining distance. After that, you cover half of the remaining distance again and again. No matter how close you get, there will always be a smaller remaining distance to cover. The problem is that this process appears to create an infinite number of steps. If you have to complete an infinite number of steps to reach the finish line, how can you ever actually get there? And yet, in real life, runners complete races all the time without any apparent trouble. This is the heart of the Zeno paradox, the conflict between logical reasoning and physical experience. To see why this is so puzzling, let's break it down more carefully. When you start the race, you cover half the distance to the finish line. Then you cover half of the remaining distance, then half again, and so on. This creates a sequence where the total distance you cover is made up of infinitely smaller pieces. 1, 2. Mathematically, this is called an infinite series. Common sense tells us that an infinite series of steps should take forever. And yet somehow it adds up to a finite result. The resolution to this paradox lies in the mathematics of infinite series. While it's true that the number of steps is infinite, the total sum of those steps approaches a finite limit. In this case, the sum of one verb. In other words, even though you're completing an infinite number of steps, the total distance you're covering adds up to a finite value, which is why you can in fact reach the finish line. But Zeno's paradox isn't just about math. It raises deeper questions about the nature of motion and reality. In the ancient world, Philosophers like Zeno and Parmenides argued that motion was an illusion because it seemed to involve this impossible task of completing an infinite sequence of actions. Their view was that the logical contradiction revealed something flawed about our understanding of the physical world. Centuries later, the development of calculus by Isaac Newton and Gottfried Wilhelm Leibniz provided a mathematical framework that resolved Zeno's paradox. Calculus allows us to handle infinitely small quantities and shows how an infinite series can sum to a finite value. But even with the mathematical resolution, Zeno's paradox continues to fascinate philosophers and physicists because it touches on the deeper nature of time, space, and continuity. Modern physics also complicates the picture. If space and time are infinitely divisible, as Zeno assumed, then the paradox might still hold. But if space and time are made up of discrete, indivisible units at the smallest scale, as suggested by some interpretations of quantum mechanics, then the problem disappears because you can't keep dividing forever. So while math may have solved Zeno's paradox on paper, the philosophical and physical questions it raises about the nature of reality remain open. Are space and time continuous or granular? Is motion a seamless flow or a series of tiny jumps? Zeno's paradox forces us to confront the possibility that even the most familiar aspects of reality, like moving from one place to another, might not work the way we think they do. The bootstrap paradox. Imagine you're a scientist who loves classical music. One day, you discover an old piece of sheet music for a beautiful violin concerto with no composer's name attached. You practice it for years and eventually perform it in public, where it becomes wildly popular. Fast forward a few decades, you're now a respected musician. A young fan asks you about the origin of the piece, so you make a copy of the sheet music and hand it to them. Years later, that same fan grows up to be a famous composer, and they travel back in time, leaving the sheet music where you originally found it. The question is, who actually composed the concerto? This is the bootstrap paradox, a time travel paradox, where an object or piece of information exists without ever being created. The sheet music has no true origin because it's stuck in a closed time loop. You learned the music from a piece of sheet music that you only discovered because it was handed down through time, but no one originally created it. The term bootstrap comes from the phrase pulling yourself up by your bootstraps, which describes an impossible task. In the context of time travel, it refers to something creating itself out of nothing. The paradox suggests that information or objects can exist without ever having been created in the first place. They are simply passed along through a loop in time. One of the most famous examples of the bootstrap paradox in fiction is found in the movie Predestination. In the film, a character is recruited into a time-traveling agency to prevent crimes before they happen. Over the course of the story, it's revealed that the protagonist's entire identity and existence are the result of a closed time loop. They are their own parent, creating a causality loop where their origin is never clearly defined. Another classic example comes from the TV show Doctor Who, where the Doctor finds a Beethoven record but realizes Beethoven never composed the music because the Doctor himself gave the record to Beethoven in the past. If Beethoven's music exists only because it was given to him from the future, where did the music originally come from? The bootstrap paradox raises profound questions about the nature of cause and effect. Normally, we think of causality as a straightforward chain. A causes B and B causes C. But in a bootstrap scenario, causality becomes circular. Effect creates cause, and cause creates effect. The sheet music example is especially troubling because it violates the principle of conservation of information. Information or matter is not supposed to appear out of nowhere. It must have an origin. But in a bootstrap loop, the information seems to materialize out of thin air. From a physics perspective, the bootstrap paradox hints at deeper questions about the nature of time. Einstein's theory of relativity allows for the possibility of closed time-like curves, paths through space-time that loop back on themselves. In theory, This could allow information or objects to be recycled through time without ever needing to be created in the first place. But this creates a troubling implication. If information can exist without an origin, it suggests that the universe might not need a beginning, that time itself could be an endless loop. The Big Bang, which we think of as the origin of the universe, might itself be the result of some form of causal loop. Perhaps the universe exists because it always has, trapped in a self-sustaining cycle of cause and effect. The bootstrap paradox also touches on deeper philosophical questions about free will and predestination. If you perform an action because you've already seen the result in the future, are you truly making a choice? Or are you simply playing out a script that was written by the loop of time? If Beethoven's music exists only because the doctor gave it to him, does that mean Beethoven was robbed of creative agency? And if our lives are governed by loops of cause and effect, does that mean our choices are ultimately an illusion? In the end, the bootstrap paradox challenges our understanding of time, causality, and even existence itself. If information or objects can exist without an origin, then reality might not be a linear story with a clear beginning and end. It could be a self-contained loop, eternally folding back on itself. And that raises the ultimate question: if the universe itself is a bootstrap loop, where did it come from in the first place? The paradox of the absent-minded driver. Imagine you're an absent-minded driver approaching a fork in the road late at night. You know that one path leads safely to your destination, while the other leads to a dangerous cliff. Before you set out on the trip, you make a plan. If you find yourself at the fork and you remember which path is safe, you'll take it. But if you're unsure, you'll choose randomly, since that at least gives you a 50% chance of survival. But here's the problem. As an absent-minded driver, you're prone to forgetting things. In fact, you know that by the time you reach the fork, you'll most likely be confused about where you are and unable to recall your original plan with certainty. The paradox emerges from the fact that your decision-making strategy seems logically sound when viewed from the start of the trip. But once you reach the fork and face the immediate choice, the logic falls apart. To see why, let's walk through the situation carefully. Before starting the trip, it makes perfect sense to create a plan. If you know which path is safe, you take it. If you don't, you flip a mental coin. But the very nature of being absent-minded means that once you're at the fork, you might not even realize that you're at the decision point, or worse, you might misremember the safe path. The paradox pedicans when you consider that from the perspective of the driver at the fork, the situation is different than it seemed at the start. If you know that you're absent-minded, then how can you ever truly trust your decision-making in the moment? Even if you're confident you remember the correct path, you might just be misremembering. So shouldn't you always choose randomly instead? But if you're always choosing randomly, why make a plan in the first place? This paradox exposes a strange disconnect between planning and execution. From the perspective of the start of the trip, the strategy seems rational and logical. But from the perspective of the fork, the very nature of being absent-minded makes rational decision-making unreliable. The paradox was first introduced by economist Robert Aumann to explore the nature of decision-making under uncertainty. It highlights a clash between two levels of reasoning: planning under certainty versus acting under uncertainty. Rational choice theory suggests that we should base decisions on probabilities and available information, but the absent-minded driver's situation shows that the context of decision-making matters just as much as the strategy itself. Aumann proposed that the problem stems from the difficulty of maintaining consistency between your global strategy, the plan, and your local decision-making, the moment of choice. If you're truly absent-minded, then you might not even recognize that you've reached the fork, and even if you do, you can't trust your memory of the plan. This means that there's no way to align the logical consistency of the plan with the flawed execution caused by absent-mindedness. There's also a deeper philosophical tension here about the nature of rationality itself. Planning requires foresight, the ability to project into the future and prepare for different outcomes. But execution happens in the present, where memory, perception, and uncertainty cloud your ability to follow through. The absent-minded driver paradox challenges the idea that rationality is purely about logic and probability. It suggests that the context of decision-making, including the limits of human memory and perception, fundamentally shapes the outcome. In a sense, the paradox reflects real-life situations where our carefully made plans crumble under pressure. Think about cramming for an exam. You might carefully map out a study plan, but once you sit down to take the test, stress and confusion could cause you to forget everything. Or consider personal commitments. You might promise yourself to stay calm in a stressful situation, but when the moment arrives, your emotions override your logical preparation. So, what's the solution? Ullmann suggested that the paradox highlights the limitations of traditional decision theory. If rationality depends not only on logical consistency, but also on context, memory, and perception, then true rationality might require flexibility rather than rigid adherence to a plan. The paradox of the absent-minded driver forces us to confront the limits of human reasoning. Sometimes the problem isn't the plan, it's our ability to execute it under pressure. And maybe true wisdom isn't just about making a good plan, it's about knowing when to trust your instincts and when to accept uncertainty. The Fermi paradox. Look up at the night sky. Thousands of stars dot the darkness, and beyond them are billions more scattered across hundreds of billions of galaxies. Given the sheer size of the universe, and the countless stars with potentially habitable planets, it seems almost inevitable that intelligent extraterrestrial life must exist. But if that's true, where is everybody? This is the essence of the Fermi paradox. The paradox is named after the physicist Enrico Fermi, who supposedly asked the question during a conversation about extraterrestrial life in the 1950s. If aliens exist, why haven't we seen any evidence of them? On paper, it seems statistically impossible for Earth to be the only planet to host intelligent life. Our Milky Way galaxy alone contains an estimated 400 billion stars. Even if only a small fraction of those stars have planets in the habitable zone, the region where liquid water can exist, there should still be millions of Earth-like planets capable of supporting life. If even a tiny percentage of those planets developed intelligent civilizations, there should be hundreds or thousands of advanced alien species in our galactic neighborhood. And yet, we've seen nothing. No signals, no spacecraft, no evidence of alien megastructures or interstellar communication. The silence is deafening. Scientists have proposed several possible solutions to the Fermi paradox. One possibility is that intelligent civilizations are simply extremely rare. Perhaps life itself is easy to start, but the leap from simple organisms to complex, intelligent life is extraordinarily difficult, a step that Earth just happened to beat the odds on. This idea is known as the Great Filter hypothesis. The Great Filter could be behind us or still ahead of us. If it's behind us, that means the transition from non-life to intelligent, technologically advanced life is the real bottleneck, and Earth already passed the test. But if the Great Filter is ahead of us, it suggests that intelligent civilizations tend to self-destruct before they can spread across the galaxy. Nuclear war, environmental collapse, or advanced artificial intelligence turning against its creators could explain why alien civilizations never seem to last long enough to make contact. Another possibility is that advanced civilizations are deliberately avoiding us, or worse, actively hiding from us. This is the basis of the dark forest hypothesis. In this scenario, the universe is like a dark forest, where every civilization is a hunter and survival depends on staying hidden. Broadcasting your location would be dangerous because any sufficiently advanced civilization might see others as a potential threat and decide to eliminate them before they can pose a danger. After all, it's safer to strike first than to risk being discovered. Or maybe aliens are already here, but they simply aren't interested in us. We could be like ants at the edge of a highway, oblivious to the existence of the larger world around us. Just as we wouldn't try to communicate with an ant colony, advanced extraterrestrial life might see us as too primitive to bother with. This idea ties into the zoo hypothesis, the idea that Earth is being observed like a nature reserve, with aliens intentionally avoiding contact to allow us to develop naturally. Another explanation could be that we're simply looking in the wrong way. Most of our search for extraterrestrial life involves listening for radio signals or looking for chemical signs of life in distant atmospheres. But advanced civilizations might communicate using forms of technology that we don't yet understand, or perhaps their existence operates on physical principles that we haven't even discovered. There's also the disturbing possibility that intelligent life might tend to wipe itself out before it reaches the level of interstellar communication. Nuclear war, environmental collapse, or runaway artificial intelligence could all be factors that prevent civilizations from surviving long enough to make contact. In this case, the silence of the universe would serve as a grim warning about the dangers of technological advancement. One final possibility is that intelligent life simply isn't interested in expansion. Maybe advanced civilizations turn inward, focusing on virtual reality or mental exploration instead of physical colonization. If technology allows them to build perfect simulated worlds, why bother reaching out into the cold emptiness of space? The Fermi paradox forces us to confront difficult questions about our place in the universe. Are we really alone, a singular accident in the cosmic lottery? Or is the universe teeming with life, separated from us by barriers of time, distance, or technology? The paradox reminds us that despite our scientific advancements, we still know shockingly little about the nature of the universe and about our cosmic neighbors, if they exist at all. The lottery paradox. Imagine you're holding a ticket for a massive lottery with 1 million tickets sold. You know the chances of winning are astronomically small, 1 in 1 million. It's entirely rational for you to believe that your ticket will not win. In fact, it's rational for you to believe that every single ticket will lose, because each individual ticket has only a 1 in 1 million chance of winning. But here's the problem. You also know that one ticket must win, because that's how lotteries work. If it's rational to believe that every ticket will lose, how can it also be rational to believe that one ticket will win? This is the heart of the lottery paradox, a conflict between reasonable individual beliefs and the logical outcome of the situation as a whole. Let's break this down step by step. Your belief that your ticket will lose is based on sound reasoning. The probability of winning is so low that you'd be foolish to expect to win. It's just as rational to believe that the next person's ticket will lose, and the next, and so on, all the way through the million tickets. From the standpoint of probability, it makes perfect sense to conclude that no one's ticket will win. But you also know that a winner is guaranteed. That's not a matter of probability, it's a fact of the lottery's rules. A winner will be drawn. So now you're trapped. It's rational to believe that every ticket will lose, but it's also rational to believe that one ticket will win. How can both of these beliefs be rational at the same time? The lottery paradox exposes a conflict between individual rationality and collective rationality. On an individual level, it's rational to believe that your ticket will lose, but on a collective level, it's irrational to believe that all tickets will lose, because that contradicts the fact that one ticket will definitely win. This paradox ties into the nature of belief and the concept of justification. Philosophers have long grappled with the idea that for a belief to be rational, it must be supported by evidence or logical reasoning. The problem here is that the evidence, the low odds, justifies the belief that your ticket will lose, but that same justification leads to a conclusion that is logically incompatible with the certainty that a winner will emerge. So how do we resolve this? One approach is to distinguish between justified belief and knowledge. It might be justified to believe that your ticket will lose, But that belief doesn't rise to the level of knowledge because you know that a winner is guaranteed. In other words, rational belief and logical certainty don't always align. Another possible resolution comes from probability theory. While it's highly probable that your ticket will lose, it's not certain, and that distinction matters. The paradox emerges from treating high probability as equivalent to certainty. In reality, no matter how unlikely it seems, there's still a chance, however small, that your ticket could win. So while it's rational to believe your ticket will lose, it's not rational to say it definitely will lose. But this introduces a deeper tension in our understanding of rationality. If rational belief is based on probability, then we face a strange situation. It's rational to believe that something will not happen and still be wrong when it does. If rationality is based on certainty, then most of our everyday beliefs, which are based on incomplete or probabilistic information, become irrational. The lottery paradox also has implications for decision-making and evidence-based reasoning. In legal systems, for example, convictions are supposed to be based on the standard of beyond a reasonable doubt. But how do you define reasonable doubt in probabilistic terms? If there's a 1 in a million chance that a defendant is innocent, is that reasonable doubt or a negligible risk? The lottery paradox suggests that even highly improbable events still carry logical weight, which raises thorny questions about the relationship between probability and justice. In epistemology, the branch of philosophy that studies knowledge, the lottery paradox challenges the idea that rational belief and logical truth must always align. If it's rational to believe that every ticket will lose, but irrational to believe that all tickets will lose, then rational belief is not necessarily a reliable guide to truth. This opens up profound questions about the limits of human reasoning and the nature of belief itself. There's also a psychological dimension to the lottery paradox. Why do people keep buying lottery tickets despite knowing the odds are against them? Part of the answer lies in the tension between probability and possibility. Rationally, you know you're almost certain to lose, but the mere fact that a winner is guaranteed allows you to suspend that knowledge and focus on the possibility, however slim, that you might be the lucky one. The lottery paradox reveals that human reasoning operates on multiple levels. On the surface level, we reason based on probability and evidence, but beneath that, we are drawn to the promise of certainty, even when it conflicts with rational analysis. The paradox exposes the gap between what we know, what we believe, and what we hope for. So, how do we live with the lottery paradox? The most honest answer may be to embrace the contradiction. We can accept that it's rational to believe that every ticket will lose, while also accepting that one ticket will win. Rational belief, it seems, is not always consistent, and sometimes the most logical approach is to hold two seemingly contradictory truths at the same time. The paradox of the infinite hotel. Imagine you're traveling late at night, exhausted, and you finally spot a hotel at the end of the road. The glowing sign reads, "Hilbert's Infinite Hotel," a hotel with an infinite number of rooms. Relieved, you walk in and ask the receptionist for a room, but the receptionist shakes his head and says, "I'm sorry, we're fully booked. Every single room is occupied." Disappointed, you turn to leave. But then, with a sly smile, the receptionist says, "Actually, I think we can make room for you." How is that possible if every room is full? Welcome to the paradox of the infinite hotel, first proposed by the German mathematician David Hilbert. This mind-bending thought experiment explores the strange and counterintuitive nature of infinity and challenges our understanding of what it means for something to be full. Let's walk through how the receptionist pulls off this trick. Even though the hotel is full, he tells every current guest to move one room down. That means the person in room 1 moves to room 2, the person in room 2 moves to room 3, and so on, infinitely down the line. This creates a vacancy in room 1. Now you can check in. At first, this seems impossible. If the hotel is full, there shouldn't be any empty room. But this paradox reveals a strange property of infinity. When you're dealing with an infinite set, you can still add more elements to it without changing its size. In other words, infinity plus 1 is still infinity. But it gets even weirder. Suppose a whole infinite bus full of new guests pulls up to the hotel. Surely even the clever receptionist can't handle that. But he smiles and says, "No problem." Here's what he does. He tells every current guest to move to the room that is double their current room number. The person in room 1 moves to room 2. The person in room 2 moves to room 4. The person in room 3 moves to room 6, and so on. Since doubling every room number creates an infinite sequence of even-numbered rooms, all the odd-numbered rooms are now empty, and there are infinitely many of them. That means there's room for every single person on the infinite bus, no matter how many guests are on it. And it doesn't stop there. What if infinitely many buses, each with an infinite number of passengers, show up at the same time? Surely the hotel would have to turn some of them away. Nope. The receptionist can handle this too. He assigns the current guests to the powers of prime numbers. The person in room 1 moves to room 2, the first prime. The person in room 2 moves to room 3, the second prime. The person in room 3 moves to room 5, the third prime. And so on. Since there are infinitely many primes, the hotel's current guests are accommodated without any conflicts. Now the receptionist starts assigning the new arrivals. He assigns the passengers from the first bus to the squares of prime numbers, the second bus to the cubes of prime numbers, and so on, effectively organizing the entire infinite influx into a structured pattern using the properties of prime numbers and infinity. Every person gets a room. At this point, your head might be spinning, and that's exactly why this paradox is so profound. In the real world, we think of full as an absolute state. If every seat in a theater is taken, there's no room for more people. But infinity plays by different rules. A set can be full and still have room for more. That's because infinity isn't just big. It's a fundamentally different kind of quantity. The infinite hotel paradox illustrates the strange nature of countable infinity, the type of infinity associated with the set of natural numbers, 1, 2, 3, 4. Even when this set is full, it can still expand to accommodate more elements because infinity has no fixed boundaries. It's not just large, it's limitless, in a way that defies our usual understanding of size and capacity. Mathematicians categorize this type of infinity as Aleph null, Alf, the smallest level of infinity. But there are actually larger infinities. For instance, the set of real numbers, which includes all the fractions and irrational numbers, is a bigger infinity than the set of natural numbers. So even in the world of infinity, there are different sizes of infinity, which makes the concept even stranger. The infinite hotel also raises deep philosophical questions about the nature of existence and the concept of infinity itself. If infinity is this strange and counterintuitive in the realm of mathematics, what does that say about the universe? Could reality itself be infinite? If so, does that mean the universe can accommodate more stuff even when it seems completely full? And if infinity can be manipulated in this way, what does that mean for our understanding of space, time, and even consciousness? Hilbert's Infinite Hotel isn't just a mathematical curiosity. It's a window into the bizarre and beautiful logic of infinity. It reminds us that some of the most basic concepts we take for granted, like fullness, size, and capacity, break down when you enter the realm of the infinite. And perhaps that's the most mind-bending part of all. But beneath the surface of our everyday experience lies a hidden reality where infinity doesn't just stretch endlessly. It expands in ways that defy comprehension. The arrow paradox. Picture an archer standing in a quiet field, bow drawn. the arrow poised in the air. The tension builds, the archer releases the string, and the arrow streaks toward the target. But now, freeze the scene in your mind, stop time at a single instant. What do you see? The arrow at that moment is completely still. It's not moving forward or backward. In that frozen instant, the arrow occupies a fixed position in space. Now imagine stringing together all the frozen moments of the arrow's flight. If the arrow is motionless in each individual instant, how can it ever actually be moving? Welcome to Zeno's arrow paradox, one of the most famous and mind-bending paradoxes of ancient philosophy. First proposed by the Greek philosopher Zeno of Elea in the 5th century BCE, the arrow paradox challenges the very nature of motion and time, and raises questions about whether motion is even possible at all. To understand the paradox, let's slow things down and walk through Zeno's reasoning step by step. Zeno argued that for an arrow to move, it must occupy a specific position at every single moment in time. At any given instant, the arrow cannot be in two places at once. It must be at one precise location. If the arrow is at a specific location, then it is, by definition, not moving. After all, motion would mean that the arrow is changing its position over time. But at any frozen instant, there is no time for the arrow to change its position. It's just sitting there. If the arrow is stationary at each individual moment in time, how can it ever be said to be moving at all? After all, time is made up of a series of these frozen instants, one after another, like frames in a film reel. But if the arrow is not moving in any individual frame, then adding up all these stationary moments should still result in a stationary outcome. A sequence of still images doesn't create motion. It just creates more stillness. To put it another way, if at every single moment the arrow is at rest, then how can it ever traverse the distance from the bow to the target? How can motion arise from a sequence of stillness? Zeno's conclusion was radical. Motion is an illusion. Our perception of the arrow moving toward the target is just that, a perception, not an actual physical process. At first glance, this conclusion seems absurd. We see motion happening all the time. We experience it constantly. Cars driving by, people walking down the street, the sun moving across the sky. Surely Zeno must have made a mistake somewhere, right? But the paradox isn't easy to dismiss, because the logic behind it is deceptively airtight. If time is made up of individual instants, and nothing is moving within any single instant, how does motion emerge from that? To understand why this is so tricky, let's consider the nature of time itself. We usually think of time as a continuous flow, a smooth river, constantly moving forward. But Zeno's paradox forces us to think of time as being composed of discrete slices, individual moments that are strung together, like frames in a film. If time really is made up of indivisible instants, then motion becomes logically impossible, because in each frozen frame, the arrow is standing still. So how can we resolve this paradox? For centuries, philosophers and mathematicians struggled with Zeno's argument. It wasn't until the development of calculus by Isaac Newton and Gottfried Wilhelm Leibniz in the 17th century that a solution began to emerge. Calculus introduced the concept of limits, the idea that an infinite series of small changes can add up to a finite result. In the case of the arrow, the key insight is that even though the arrow is technically at rest at each individual instant, the overall position of the arrow is changing over a continuous period of time. The motion isn't defined at a single instant. It's defined by the limit of the arrow's changing position over the sum of those instants. The arrow isn't moving within an instant. It's moving through the series of instants, and the mathematical framework of calculus allows us to calculate exactly how that happens. But even though calculus helps us mathematically describe motion, it doesn't entirely dissolve the philosophical weight of the paradox. Zeno's argument forces us to confront the strange nature of time itself. Is time truly continuous, Or is it made up of discrete moments stacked together? If time is continuous, how do we account for the fact that the arrow appears still in any single frozen instant? And if time is made of discrete parts, how can motion emerge from a series of still moments? Modern physics adds another layer of complexity to this puzzle. In quantum mechanics, time and motion are not as straightforward as they seem. At the smallest scales of reality, particles don't move in smooth, continuous paths. They jump and shift in unpredictable ways. This suggests that Zeno's paradox touches on something deeper about the fundamental nature of reality, that motion and time might not work the way our everyday experience suggests. The arrow paradox isn't just a mathematical or philosophical puzzle. It's a challenge to our most basic understanding of how reality functions. It asks us to reconsider the nature of time, motion, and continuity, and to question whether our intuitive grasp of movement is actually an illusion. So the next time you see an arrow flying through the air, or a car speeding down the highway, or even a leaf drifting in the wind, stop and ask yourself, is it really moving? Or is it just a series of frozen instants, stitched together by the illusion of motion? That's the unsettling brilliance of Zeno's arrow paradox. It transforms something as ordinary as movement into a profound mystery about the fabric of reality itself. The paradox of choice. Imagine you're standing in the middle of a supermarket aisle, staring at an overwhelming wall of salad dressings. Ranch, Italian, Caesar, balsamic, honey mustard, blue cheese, dozens of choices, each with subtle variations. Low fat, organic, gluten-free, the options seem endless. You pick up one bottle, then another, trying to decide which one is best. Minutes pass. Frustration builds. Finally, you grab one at random, walk away, and immediately start wondering if you should have picked another. Sound familiar? This is the paradox of choice. The idea that while having options is supposed to make us feel more free and satisfied, too many choices can actually leave us feeling stressed, anxious, and even paralyzed. It's a modern dilemma, born out of abundance, and it raises the question, is more really better? This paradox was popularized by psychologist Barry Schwartz in his 2004 book, The Paradox of Choice. Why more is less? Schwartz argued that while freedom of choice is a cornerstone of modern society, something we associate with autonomy and happiness, too much choice can backfire. Instead of feeling empowered, we become overwhelmed. Instead of feeling satisfied, we feel regret. To understand why, let's break down how our brains handle decisions. When faced with a small number of options, say, choosing between 2 or 3 flavors of ice cream, the decision-making process is relatively straightforward. You weigh the pros and cons, make a choice, and move on. But when the number of choices increases, let's say you're choosing between 31 flavors, the cognitive load skyrockets. Suddenly you have to compare and evaluate a much larger set of options. The mental effort increases exponentially. At first, this abundance of choice feels exciting, but soon the excitement gives way to anxiety and analysis paralysis, a state where you feel stuck because there are too many competing options. Psychologists have identified 3 main reasons why too much choice leads to unhappiness. First, decision paralysis. When you have too many options, your brain struggles to process the information efficiently. Studies have shown that when consumers are presented with a large number of options, they are significantly less likely to make a purchase. In a famous experiment conducted by psychologists Sheena Iyengar and Mark Lepper, shoppers were offered samples of jam at a grocery store. When only 6 flavors were available, 30% of shoppers made a purchase. But when 24 flavors were available, only 3% bought anything. More choice led to fewer decisions. Second, increased dissatisfaction. When you finally make a choice from a large set of options, you're more likely to feel unsatisfied, even if the choice was objectively good. Why? Because with so many alternatives available, your mind starts to wonder if you picked the best option. If you buy a chocolate bar and it's not perfect, you can't help but think that one of the other flavors might have been better. This creates a lingering sense of regret and doubt. Third, self-blame. When you have only a few options and the outcome isn't great, you can blame the situation. Well, there weren't many choices, but when you have dozens of options and the outcome isn't perfect, you blame yourself. Why didn't I pick the better one? The more choices you have, the more responsibility you feel for making the right decision, and the more pressure you feel to get it right. But here's the twist. It's not just about consumer goods. The paradox of choice applies to life decisions too. Think about relationships. Dating apps give you access to hundreds, even thousands of potential matches. On the surface, this seems empowering. More options should mean a better chance of finding the perfect partner, right? But in reality, it creates the opposite effect. When you have so many choices, you're more likely to hesitate, overthink, and fear commitment. And when you do commit, you might feel like you've settled, because there's always the nagging feeling that someone better might be out there. The job market works the same way. With so many career paths, industries, and remote work options available, young professionals often feel stuck, not because they lack opportunities, but because they have too many. What if you pick the wrong field? What if you take a job and miss out on a better one? The fear of making the wrong decision becomes paralyzing. Social media amplifies this effect even further. Platforms like Instagram and TikTok constantly expose us to the curated, polished lives of others. You see someone traveling the world, someone else getting promoted, another person getting married, and suddenly you feel like you're falling behind. The sheer number of possible life paths creates a sense of anxiety and inadequacy. If other people are making seemingly perfect choices, why can't you? Barry Schwartz's solution to the paradox of choice is counterintuitive: limit your options. He argues that happiness comes not from having unlimited choices, but from simplifying your decision-making process. Instead of trying to find the best option, aim for a good enough option, a strategy called satisficing. When you satisfice, you focus on finding an option that meets your needs, rather than obsessing over perfection. For example, instead of spending hours comparing every possible restaurant in town, you could decide to eat at the first place that looks decent and has good reviews. Instead of endlessly swiping on dating apps, you could commit to exploring a connection with one person who meets your basic criteria. Instead of trying to figure out the perfect career, you could aim for a fulfilling job that aligns with your values, even if it's not your lifelong dream. Schwartz also recommends setting personal limits on choices. For example, you could decide to only browse 2 job sites when job hunting, or limit yourself to 3 streaming services, rather than subscribing to every platform. These artificial constraints reduce cognitive load and make decisions more manageable. Interestingly, research shows that people who deliberately limit their options tend to feel more satisfied and less regretful about their decisions. By reducing the number of available choices, they experience less analysis paralysis and more confidence in their decisions. But there's a deeper philosophical question beneath the paradox of choice. If more options don't make us happier, why do we crave them so much? Part of the answer lies in the human desire for control. We associate choice with freedom and autonomy, the ability to shape our own destiny. But when the number of choices exceeds our cognitive capacity to process them, that sense of freedom turns into a psychological burden. The paradox of choice teaches us that more is not always better. True freedom doesn't come from having unlimited options. It comes from having enough clarity and confidence to make decisions without regret.
In a world overflowing with choices, sometimes the best decision you can make is to simplify your options and trust that good enough is in fact good enough.